Okay, in this segment we're going to finish up talking about the differential pair. There's a couple of loose ends I want to go back and talk about, and then we're going to talk about strong inversion operations, so the diff pair. So before we had this circuit, which we're going to continue to talk about. So let's put it up here. So we have here our two matched transistors. They're sharing the bias current that's being sunk by the bias transistor. And what we found was that depending on the values of V1 and V2, this bias current would be steered to more to the left or more to the right. We did a large signal analysis of the operation of the differential pair with a weak inversion bias current. Last time, we want to finish up a couple of things there. One thing I forgot to emphasize, and that's one of the key important things about the diff pair, is that the diff pair has a large response to changes in VDM and almost no response to changes in VCM. Okay, so remember last time we introduced the differential mode voltage, which is the difference between V1 and V2, and the common mode voltage, which is the average value of V1 and V2. If we move V1 and V2 relative to each other so that they're moving and the difference is changing, the current steers back and forth, and we get a large response in the currents. Whereas if we move the two up and down together, like so, the current balance stays basically the same. If we took V1 and V2 and tied them to the same place, that's a pure common mode input. So the average value is just the value of each of them. We move that up and down together. The bias currents would be split 50-50 between the two sides, and that bias current, half IB, half IB, would be the current out. Okay? And so the differential current, the I1 minus I2 output current, would just be zero. There'd be no response. And that is really the most important property of this circuit, and why it's used as the front end, the input stage to pretty much all sorts of differential amplifiers that have been built, because it selectively amplifies or selectively responds to changes in the difference between the two inputs, regardless of changes in the common mode. Okay, so that's an important thing to bear in mind or to remember about this circuit. What I want to go back and tie up as a loose end is the behavior of this common source node voltage V. Okay, we wanted to eliminate that from our description of the system before, and we will not often have occasion to use the behavior of that node voltage in making, let's say, an op amp or something like that, or using this as a transconductance stage. But there are contexts in which that voltage is actually a useful thing in its own right, and it's important to kind of have an intuition for what that voltage is doing. So if you recall, at one point in our analysis, we had written down that the weak inversion saturation model for MB implied that IB was equal to SIS e to the kappa VB minus VT0 over U ut. That was one equation that we had never really gotten around to making use of. And then at one point in the analysis, we had this equation that said something like, see, it was IB equals SIS E to the minus kappa VT0 over UT times e to the minus v over ut times e to the kappa v1 over ut plus e to the kappa v2 over ut. We had taken the KCL equation and substituted in the I1 and I2, and we had factored out the common stuff, and then we took this stuff down to the other side and we substituted this out of the I1 and I2 to eliminate v. Well, now we're going to use this equation in conjunction with this equation to try to get an expression for what v does as a function of v1 and v2. Okay? So to do that, we're going to substitute in IB on the left-hand side here for what's on the right-hand side. And that's going to give us SIS e to the kappa VB over ut times e to the minus kappa VT0 over ut on the left-hand side is equal to, well, we've got some common stuff here, SIS e to the minus kappa VT0 over ut times e to the minus v over ut times this thing in parentheses, e to the kappa v1 over ut plus e to the kappa v2 over ut. And here we can cancel some stuff on both sides of this equation. We can cancel the SIS, we can cancel the e to the minus kappa vt0, and we can use this equation to find an expression for v as a function of vb and v1 and v2. Okay, so to do that we can move the e to the v over ut from downstairs over on the right hand side to upstairs over on the left hand side, and that becomes e to the v over ut is equal to, well, we got this stuff in parentheses here, e to the kappa v1 plus e to the kappa v2, and then we can move this e to the kappa vb over ut over to this side, and that becomes e to the minus kappa vb over ut. Now we want to solve this equation for v, and we can do that by taking the log of both sides, right? So the log of e to the v over ut undoes the exponential here, and we get v over ut. We can move the ut to the other side, and then we can take the log of this side, right? And we can use some properties of logarithms. So the log of a product is the sum of the logs, and the log of e to the minus kappa vb over ut would undo that exponential factor. And so applying all of those steps, we can write this as v equals ut times the log of e to the kappa v1 plus e to the kappa v2, and then having broken out this factor as a separate sum of log, having undone the exponential with the log and canceling the ut, we have minus kappa times vb. And so this is our equation for v as a function of v1, v2, and vb. Now this is a very interesting function, and we've met this function before. This log ut times the log of e to the something over ut plus e to the something else over ut is something we call the soft max of these two things. So this is equal to, so V equals the soft max of kappa V1 and kappa V2 minus kappa VB. And of course, if we wanted to, we could factor out the kappa, right? Because if we have the soft max of kappa V1 and kappa V2, that would be kappa times the soft max of V1 and V2. So this is equal to kappa times the soft max of V1 and V2 minus VB. So how does this thing behave? Well, let's make a sketch of V as a function of, let's say, V1. And we'll say that VB might be down here. And let's say V2 happens to be, oh, I don't know, right here someplace, V2. And let's say VDD is here. Draw a box. Draw our identity line. Like so. V equals Vn, or V1 rather. And so I'm going to draw here a line which would be if M1 were a source follower and M2 were not in the picture, the source follower characteristic would look something like this. Right, so this would be slope of kappa and it would extrapolate down to VB, and it would smoothly approach 0 down here below VB. What will happen is that when V1 is less than V2, what we're going to get is the V2 popping out of the soft max. And so we get kappa V2 minus VB. So it'll be a constant value that it has. And that's not very good. So this is kappa V2 minus VB. And once V1 exceeds V2, then the soft max will transition smoothly over to V1, and we're going to follow this V1 minus VB times kappa. And so we join up with this source follower transfer characteristic after V1 exceeds V2. So before V1 gets to V2, the common source node is just constant at this value, kappa V2 minus VB. But once it exceeds, V1 exceeds V2, we switch over to following the source follower transfer characteristic. And that's what the common source node will do. So when V2 is higher than V1, essentially M2 is winning. So if you think of this diff pair as a competition between two source followers, M2 is getting all of the bias current, M1 has got almost no bias current, and M2 is getting to dictate what this common source node voltage is doing. Oh. That's unfortunate. Let's prevent that from going to sleep again. Well, hopefully that's not too much. So just recapping here. When V1 is less than V2, V is going to be at a constant value of kappa V2 minus VB. And then when V1 exceeds V2, what happens is we smoothly join up with the source follower VTC that V1 would have if M1 were just a plain old source follower. And so, sorry for the blackout there. So as I was saying, when V1 is less than V2, all the current is steered over to the V2 side, and the source follower M2 gets to dictate, is winning the competition here between the two source followers, and gets to dictate what V is doing. When V1 exceeds V2, we switch the bias current over to the M1 side, and we wind up with M1 controlling what V is doing, and so then we start joining up with the source follower transfer characteristic that M1 would have. Okay. One other thing to note here is that V is got a lower bound. V is always greater than or equal to kappa times the max of V1 and V2 minus VB, right? So the softmax function is always strictly greater than max. So the max function would be a perfectly straight line here, and then it would join up with a perfectly straight line here that is going up with a slope of kappa, and they would join at a sharp corner here, so the max function is not differentiable, but the softmax function is above it, and it has some what would be called corner error. And so the maximum deviation between the max and the softmax occurs at V1 equals V2, and in weak inversion it's not very different. They're not very different from each other. They differ by a factor of like UT over kappa times the natural log of 2, which is actually a fairly small number. It's like in the range of 20 millivolts or less. And so this is actually a fairly tight lower bound on V in weak inversion and moderate inversion too. When you get into strong inversion, you get qualitatively similar behavior for the node voltage V, and this is still a lower bound, but it's not quite as tight a lower bound because this corner error is larger and it takes more voltage difference to do the switching over from one to the other. The corner gets more rounded and the corner error gets a little bit more pronounced. So this lower bound is still a lower bound, but it becomes a more looser lower bound in strong inversion operation. So that's another useful thing to bear in mind. Okay, so that's you can actually use this circuit if you need to build something like a maximum circuit. It is possible to use this differential pair and the common source node voltage as a basis for building a maximum circuit, which is kind of a cool thing, but it's not a mainstream sort of application. But I just wanted to show you that there is a circuit that embodies the softmax function that we've talked about a couple of times. Okay, so now we're going to very briefly talk about strong inversion operation of the diff pair. we have the actual large signal analysis covered in the course notes, the packet, and we're not going to repeat that in class. Rather, I just want to spend a little bit of time kind of going over 2 or 3 slides here that kind of compare and contrast some things about the above threshold operation of the diff pair, strong inversion operation of the diff pair. So what I've got here in this first slide is a family of characteristics where I've normalized the difference between I1 and I2 to the bias current. And so here the bias current is changing from weak inversion through moderate inversion up into strong inversion, and for increasing IB, these curves basically start stretching out. So all through weak inversion and into moderate inversion, these curves are all basically on top of each other, just like the drain characteristics. If we were to normalize the drain characteristics by their saturation current level, all of them would saturate in about 100 millivolts or so. And that's very similar to what we would see here for this hyperbolic tangent saturating S-shaped nonlinear characteristic we have for the differential pairs output current, differential output current versus V1 minus V2. They would all lie on top of each other. And then as we start going above threshold, just like in the drain characteristics where it would take more voltage to saturate the transistor, we would have a wider kind of transfer curve here and a more linear transfer curve. So whereas it takes about only plus or minus maybe 50 millivolts to go through this sort of transition region from being saturated at minus IB to being saturated at plus IB for weak and moderate inversion, when you get to, let's say, a volt or so above threshold, it takes plus or minus a volt to actually saturate, to make the transition from minus IB to plus IB. And so that's a key difference between the two. So if we were to take one of these strong inversion curves and make a hyperbolic tangent whose slope of the tangent line here at the origin matches the above threshold diff pair characteristic, what we find is that if you imagine this is a linear transconductor here that maybe clips at some point, so that there's a straight line transfer characteristic here, the above threshold characteristic stays closer to that straight line for a wider range of voltages than the hyperbolic tangent does, even though they have the same slope of the tangent line here at the origin. What that means is that if you imagine sort of the Taylor series expansion for each of these two characteristics, there would be a linear term and a cubic term and a fifth order term and a seventh order term, all the odd order terms, because this is an odd function, an odd symmetric function. The coefficients of that cubic term would be smaller for the above threshold diff pair than it would be for the hyperbolic tangent. And likewise, probably the coefficient of the fifth order term would be smaller, and the coefficient of the seventh order term would be smaller. And what that translates into is you can put in a larger sine wave, let's say, pure tone sine wave, larger amplitude pure tone sine wave, into the above threshold diff pair, and you would get less harmonic distortion out than if you were to put it into a kind of a stretched out weak inversion transfer characteristic. Okay, so that's what I mean by a softer nonlinearity or less nonlinearity, right? So for the above threshold transfer characteristics, these are better approximations to a straight line over a wider range of voltage than the hyperbolic tangent. And that's important for building things like filters, linear filters that are meant to do linear processing of, let's say, audio signals or other kinds of signals. So that's one key difference. The other thing has to do with the modeling. So once you go to the trouble to actually do the large signal analysis of the differential pair above threshold, you basically make the same kind of assumptions that we made for the weak inversion analysis that we did. You say, let's assume that all three transistors are operating in strong inversion. Let's write down the IV relationships based on the EKV model in saturation. Let's apply KCL at the common source node. Let's eliminate V from the description. You wind up having to solve a quadratic equation, bust out the quadratic formula, collect a lot of terms. And once you do that, you get this kind of expression for the differential output current here. You get it's proportional to the differential mode voltage, normalized by how far above threshold you are, times this square root of a constant minus the square of the differential mode voltage, normalized by the same factor here. And then if you basically plot this expression as a function of V1 minus V2, you get this kind of weird dashed curve. So it follows quite nicely the measured characteristics that you get for a while, but then it turns around and then actually eventually becomes imaginary, right? So this term, when this exceeds 2, this becomes the square root of a negative number, and it winds up being imaginary. So the question is, why is this the case? Why does this model come with some conditions on its limits of applicability? So this model has limits on the maximum input differential voltage over which it applies. What breaks in the model? So if we were live in class, I would probably give people an opportunity to talk to each other about that. And if you want to think about that for a minute while you pause the video and then come back, you can do that. But basically the idea here is that when you're in this intermediate range, okay, in this middle area, both of the diff pair transistors are operating with about half of the bias current. And if that bias current is in strong inversion, then half the bias current will also probably be in strong inversion. And then as we move further away from the center here, you're starting to steer some of the bias current over to one side. So in this part of the curve, it would be over to the I1 side. If you're in this part of the curve, it would be over to the I2 side. But eventually what happens is that M1 would get more and more and more of the bias current until it gets all of the bias current, and M2 would get less and less and less. And eventually, as M2 is getting less and less and less current, its current level goes from being in strong inversion into moderate inversion. And at that point, our initial assumption that the I2 current is described by the above threshold model becomes invalid. And so M2 will be switching over into moderate inversion and into weak inversion by the time we get up here. And so that strong inversion model no longer applies and no longer well describes what's going on in the transistor. And so that's why we get this turning around and eventually it going imaginary. Over here, it would be M2 that's getting all the bias current and M1 that is going into moderate inversion and weak inversion by the time we get down here. And so that's what breaks here with the above threshold diff pair model. So this equation is not super important. It's doable. You might wonder, is it possible to do a large signal analysis of the diff pair transfer characteristics with a full-on EKV model, the log squared 1 plus e to the x over 2 that would hold in moderate inversion and wouldn't be subject to this kind of breakage that we see with the above threshold model? And it is not possible to do the voltage to current transfer characteristics using the full-on EKV model. It is possible to do the current to voltage transfer characteristics, i.e. if you give me a pair of currents and the bias current, it is possible to basically solve for the differential mode input voltage that would give you that situation. So you can solve the equations and work the math out using the full-on EKV model for the inverse diff pair transfer characteristics, but you can't do it so for the forward transfer characteristics, which is unfortunate, but that's the way it works out. So anyway, that's it for the diff pair, and next time we're going to talk about a simple differential amplifier comprising an NMOS differential pair with a PMOS simple current mirror that we're going to put on top to take the differential output current of the diff pair and turn it into a bidirectional output current of an amplifier. Anyway, so we'll see you next time.